Hi, it's the definite integral in 5.2. There's not much to this one, but it is a lifesaver because what we just went over in 5.1, finding left, right, however many rectangles, finding those heights, is a lot of work. And what we ended with was a summarization of what would be ideal is that we had infinitely many cuts or rectangles to that area and that width from A to B on that closed interval, because then the approximate will get very close to the exact. And so what we decided was that we would do it for one section, and that's it. 5.2 is titled the definite integral because it is going to be defined over some interval, all right? Meaning that we will have from some number to another, A to B, to find this now means the area under the curve, just like the derivative meant the slope of the tangent. But this was a lot to do. We didn't want to find the heights and that common width for all of our rectangles. However many was too many. And we said as many as we possibly can would be the best. So we were allowed to replace all of this with this over our closed interval and still find those lengths and widths, just written in a different format. And that, my friends, is called the definite integral, the namesake of this section. So let's highlight that. And remember, to find those widths, it was always the interval divided by the number of rectangles that we were going to use. Now recall that we called the integral the antiderivative of a function. And all we knew was that we were working backwards from the derivative. And so when we provided the antiderivative in that last section of chapter 4, 4.10, we realized that we could just take the derivative to see if it was true. But we didn't really know what it found until this chapter. We now know that it finds the area under our curve from two endpoints, A to B. Now remember when we were doing the antiderivative stuff in chapter 4, we always had to worry about that constant that could be there. But with these, because we have it defined from or over some interval A to B, then what would end up happening is that those constants are then going to cancel out. So we're going to have to start paying attention to, are they just asking us for the antiderivative to just integrate, or is it now defined over some interval that they now want us to find that area under the curve for there, not just what the antiderivative is. And what was really important for us as we were working through the derivative in both chapter 3 and its applications in chapter 4 was that we had a continuous function on a closed interval. No different. Here's our first theorem, 522 in this section. Because if it's continuous on that closed interval, then what will we be able to do and find on that closed interval? We can integrate and find that antiderivative or area under the curve. We therefore say if it's continuous on that closed interval, then it is integrable. I know, more crazy terms in vocab. Right? So again, very, very important whether we're working with a limit or a derivative or now the antiderivative, because limits approach from both sides and derivatives and integrals are just limits in disguise that find particular things. That's why this is so very important for us to know. Now, it doesn't mean that they're not integrable if it's not continuous, but it definitely helps. So we want to talk about how to evaluate that definite integral. How do we find that area under the curve using this shortcut of integration rather than that Riemann sum approximation? But we're not quite there yet, unfortunately. We're going to continue to use geometry and those rectangles or other shapes that we know and hopefully can think of without graphing in order to find the area over some interval. So let's take a look at a few more definitions before we move on. The first one, 523A, is called the net signed area. And as long as it is continuous, then we know it's integrable on that closed interval. And if we have two different areas for this function, one that lies above the x-axis and another that lies below it, then what would we have to do in order to combat that negative values down below? We'd have to throw a negative in front of it. So as you know that functions are both above and below, sometimes all above, sometimes all below the x-axis, then when we say to find the area under it, it's always to the x-axis, which means some of these things will come out negative. Most will come out positive. Some will even come out zero, meaning they flatline on the x-axis, amongst other things. We'll talk about the different scenarios of this. But if the culmination of all of this versus all of that, in other words, the positive area versus the negative area, when we combine those, then we will either end up with a positive total area, negative, or even zero if they are the same. So this is also called displacement. And that may not make sense to you yet, but we will make sense of it a little bit later in this chapter. Because remember what the antiderivative does to a function. As an application, for example, if we had velocity as our function and we took the antiderivative of it, then that's going to yield a position function. And if we're looking at it from A to B for our time, then we would be evaluating this from A to B, which is really going to give us our starting position versus our ending position, which, if you find the difference in those from where you started to where you ended, that is what is called displacement. That is different than part B of this, which is titled the total area. The total area is a bit different because I don't want to just know, like in displacement, where I started to where I ended. The total area, I want to know all of the places I went. And you may have gone forward and then backwards and then forward again. And your displacement would have given you the difference between these 2 points. But what about all of this other distance that I went that you only counted one time to get from there to there? That's what we mean by total area, which means we want to get rid of the sign, the positive versus negative. We want for area, all of it to be positive, which means we will have to take the absolute value of our function. And therefore, we want to find where that thing would be equal to zero. Because if we know where it's equal to zero, then we can test about that to see if both things are positive or if one's positive and one's negative. And what would we have to do to this in order to make sure that we got our area, which was always positive? We'd have to combat that negative with another negative like this so that we get a positive result. Okay, so that's the main difference between these, is that we will find for the total area only the positive things. Where the displacement, we're finding the difference. So before we move on to some examples of these types of things, I wanted to give you a few more definitions that I'd really like you all to try to figure out what the results would be before I just give them to you. Now, we will eventually get to a more calculus approach of all of this, but I wanted you guys to think these through. So do me a favor, pause it right here, see how much of this that you can reason through, knowing that this symbol means not just the antiderivative anymore, that integral, it means the area under the curve. For this one, from there to there, there to there, there to there, of these different things. So do yourself a favor, pause it here, and see if you can't come up with what the results would be before I give them to you. All right, I hope you gave yourself some time to think these through, because that will help you to grow even more than just copying them down and knowing them based off of my notes. What is this first one saying? Find the area of our function, our y value, our length and our width from A to A. That's at the exact same point. There is no interval. It's the same. So will there be any area under the curve from A to A? No. The answer to that one is just 0. But what about a constant? What if that was our y value? Well, then you know that it's going to look like this. And graphically, that means we'd go up C. And from A to B, this one is saying, we would draw our line, our constant, where y is equal to that thing everywhere, and we would drop from there to there. And you can see that you've created a rectangular shape, maybe even a square for my quick little drawing. Either way, we know the width of this would be B minus A, and the height of this thing, the length, would just be whatever C is. That's how far up you want to find that area. So now hopefully you can see that the answer to this one should be whatever that height would be times your width, your two endpoints. Now typically we put the smaller one on the bottom, bigger one on the top, so that we can do the top minus the bottom to get a positive result because we're finding area. And if it's above the x-axis, then we know it should be positive. But what if there's a negative out in front? You may have even missed it. Well, we know that to mean the opposite in math. And if we're going to find the opposite, then that means we can just take our endpoints and reverse them. So this one, a little tricky if you didn't quite get this one, I get it, but it is just the same height and width. But to get rid of that negative out in front, or sometimes you're going to want to put it so that you can switch these around, we will then have the A up top and the B down below, the opposite for our upper and lower limits. Now, if we had two functions that we were adding together, whether we actually could add things or not, same with subtracting, remember these are just limits in disguise. So we can actually just take the limit of each function, and therefore we can do the same with these integrals. So this one would just be the integral of f of x dx from a to b, and then added by g of x dx. Same thing with the subtraction. The only thing that would change is the fact that it would be a negative sign, which if you wanted to add, just like we did before, you could take this, make it addition, but you'd have to do the opposite for your upper and lower limits. Now again, because these are limits, remember anytime we had a constant, we could just pull that out in front. So if you got this one, it should have been where we're simply just pulling that constant out in front and evaluating the things with the variables that will actually vary. This is just going to make it that times bigger, which if we just find this and then multiply it, it'll still be that much bigger. The last one here, if we went and took the same heights and widths, but found the area under the curve from A to C, and then C to B, think about what that would mean. If we went from A to C and then C to B, ultimately we're finding the area of all of this. We're just doing this one first and then that one second. So if you didn't want to have them split, or if you actually needed them split, you can go left to right or right to left. Either way, for this one, we can combine these to get from A to B. Now, like I said, most of the time we will not go that direction. We'll actually be going from right to left, where we have this, don't want that or don't have it, and so we can split it up from some place in between A and B and find each of those that we do know or want or have. We'll get into this a little bit more as we progress, but these are just ideas of, they're just our limit rules or definitions, but applied to integrals. All right, well, we got one more definition before we can get moving on these things, and let's get through 5.2, titled the definite integral, so we can start actually utilizing these things in the best form. Almost there. Second section coming to a close with this definition 5.2.5. Again, notice stating it has to be continuous on a closed interval. Then we are able to find what is called the average value of this function, or what they will label it as is, for the function, the average. I call it my fave because it looks like that, but still just finding the average of this. And remember, if we're finding the area under the curve, if we had some sand that we brought home and it was in a bottle and it was kind of like this going down, well, if we shook that bottle, then what's going to happen is this is going to kind of average out to some middle. And that's basically what this is finding for us. Not something that we use often, but one last definition of things that we need to at least have seen. So the average for any function can be found by doing the same thing that we've always done. But remember, this is going to find just the area under the curve. We want the average of it. And in order to find averages, we have to divide. And what are we going to divide this by? Since it's going from A to B, that width, we will simply just divide by those widths. That's it. Now we just need to practice these different techniques, definitions, before we get to integrating these in the best, fastest way that we can. And when we're able to do things like that, then they're going to start throwing other more challenging ways and looks of these. So don't hold your breath until you get there, but continue to work hard. Try to comprehend this to the deepest level that you can, and we will continue to push the envelope of ability. Till the next one, take care, everyone. Alan, signing off. See ya!